evaluate this line integral where C consists of the line segments from 0, 0 to 2, 0. So 0, 0, that's the origin, and 2, 0 here. So we have a horizontal line segment, and from 2, 0 to 3, 1. So that's another line segment. We can say first line segment is C1 and C2. So our C is in fact C1 union C2. So to find this line integral, we can find the corresponding line integrals at C1 over C1 and C2 and add them. Okay, so at C1, so let's parameterize this curve. C1, just a line segment from the origin to 2, 0, 0, 0 to 2, 0. If you look at closely, y coordinate is not changing, so y is 0. I mean, that's the equation. That's the equation of this line. Anyways, y 0. Then x is anything, just take t. Or we could leave x as itself, x, but let's take x equals 2 and look at closely 0, 2. So x runs from 0 to 2. So that is t now, runs from 0 to 2. In the same way, let's do this parameterization here. On C2 curve, that's 2, 0 to 3, 1. So whenever we have 2 points, then what we do, we write down first point times 1 minus t plus second point times t. Okay, that way when t runs from 0 to 1, we get first point and second point. So the parameterization xy is equal to first point times 1 minus t plus second point times t. Now x is just the first component, so x equals 2 times, we just distribute 2 times 1 minus t plus 3 times t, the first components, and let's simplify. This is 2 minus 2t plus 3t minus 2t plus 3t is plus t, so 2 plus t. So x equals 2 plus t. In the same way, y equals second coordinates now, and the second coordinates are y here, 0 times 1 minus t, which is 0, plus 1 times t, so just t, so y equals t. And this type of work, always t is from 0 to 1. Okay, so let's find the line integral on first segment, line segment or curve. Okay, so in this case, over C1, we need to find, let's find the square root, because when we change ds into dt, we need this quantity, which is x prime t squared, that's dx over dt squared, plus y prime t squared, which is, find the derivative of x, which is a derivative of t with respect to t is 1. So this is 1 is squared plus 0 is squared, just 1, and the square root of 1 is 1. Okay, then over C1 of square root of 2x y ds, this will be same as, now look at here, this parameterization, t runs from 0 to 2, so this will be 0 to 2 root 2 times x is just t times y is 0. Okay, y is 0, and this is 0 means everything 0, we don't have to do anything in fact, times this 1 dt, so this is just 0 because we have the integrand 0, so this is 0. So let's work on this segment now, C2. Again, we need to find this quantity, x prime t squared plus y prime t quantity squared, which is derivative of 2 plus t with respect to t, because this is the x, 0 plus 1, 1 is squared 1 plus this is derivative of t is 1, so 1 is squared, just 1, and which is 1 plus 1, just root 2. Now we can integrate over c2, and the question is root 2xy. So this is root 2x, x is 2 plus t times y is t times this quantity root 2 and dt. Okay, this is in fact equals ds. Now let's, c2, I should have written the bounds for t. Look at here, t from 0 to 1, so this is 0 to 1, so pretty much calculus 1, and this is, we can multiply root 2 and pull outside 0 to 1, so we have 2 plus t times t, we can distribute, so 2t plus t squared dt. Let's use the power rule. 2 antiderivative of 2t is just t squared plus antiderivative of t squared is t3 over 3, and we go from 0 through 1, that is 2 times upper limit minus lower limit. Upper limit means t equals 1, so 1 is squared, 1 plus 1 cube 1/3 minus 0 plus 0, no contribution from bottom. 2 times from lower limit, 1 plus 1/3 is 4/3, so that is 8/3. So thus the total integral of the given function root 2 x y ds is over c1 and over c2. That's first part is 0, second part is 8/3, so the final answer is 8/3.